Our next participant will continue the subject that Alexei started. We'll be talking about robotics. So, dear friends, our next speaker is Aleksandr Gamayunov, leading developer and engineer of the Center of Robotics in Sberbank. Dear colleagues, I am the engineer at the Lab of Robotics in Sberbank. In addition to engineering, another thing that we do is research. And let me share the results of such research. The research of navigation of mobile robot. Navigation is a broad term, and it includes both tasks to build a mapping, and regulation of the speed of the movement of the robot. I love to split the navigation task by the colleagues from the Texas University. This is their latest research, where they split the navigation pipeline into three major sections: global planning subsystem, navigation pipeline, and local planning subsystem. So at the stage of global planning system, the perception part, the data from sensors is being processed into two maps. One global map with static obstacles and local map. A small map with only current range of view of the robot. So the global planner, knowing the objective of where the robot needs to get, builds therefore a route for movement based on the global map, seeing the coordinate sets. That coordinate sets are sent to a local planner, which in turn take into account the dynamics of the robot, and the local map builds trajectory of its movement. A local planner, in addition to everything, also tries to avoid collisions with dynamic obstacles. That's where our research area begins, because human being is not just a dynamic obstacle. It's an obstacle that is hardly predictable by the person, him or herself. Because people may bump into one another. And that happens not that often with a robot. So we're trying to predict the movement of a human being. So here where we are, this is the expansion of the local representation in the map. Let me say a few words about the types of human motion prediction. We have 8 coordinates of observation of human being. We need to prevent next 12 points based on this point map, so we can compare it to the real ones from the data set. Why is it like this? Well, this is historically like with the Leno image from computer vision. If you want to compare your algorithm with the other algorithms, you need to be using the same data. So let us predict the trajectory of the human being. We can do it differently. For example, we can approximate the dynamics of the movement of a person and build a person's trajectory. Unfortunately, for that type of approach, you need to know the final endpoint where the person needs to get. The classical approaches, in addition to that, are not with the fashion at the moment. Neural networks are much more fashionable today. Having trained them, you can get a better result. By the way, how do we evaluate the result of this sort of forecast? We take into account geometric errors between the forecast and between and the actual position of a person throughout the entire trajectory. So it can have average displacement error, and final displacement error is for the final point in the coordinate system. Neural network-based approach have significantly improved these parameters lately. But in addition to the most probable trajectory, they can also predict 2, 3, 5, 10, the most probable trajectories that we can use. But it's hard to say what amount of them we need. By the way, in addition, at the next stage of planning of the trajectory for the robot, it's very hard to take into account all of this a web of predicted trajectories and build the route. In our work, we decided to go the other way. We have tried our best to evaluate the quality of the predicted trajectory, build predicted trajectory, and trying to evaluate the error based on the 2D voice distribution. Statistically, we can say that if, for example, this distribution is normal, then in the radius, the probability of getting the actual position of the person into the forecast in the radius of 1 sigma is 39%, while the probability that the actual position of the person is in the radius of 3 sigma must be 98%. This is our target. In order to check how the current approaches can tackle this, we can try to forecast this radii of sigma based on dataset and compute what's the actual number of positions are within the radii. Let's call this matrix part of prediction errors inside alpha sigma radii. So we have tried the most widely spread trajectory forecast options. We're curious about the two last columns here. As you may see, the first and the last approaches of forecast have given us a significantly lower number of matches. 4.7%, 8.2% in the radii of 1 sigma when we seek to 39%, and 10 and 20% in 1 sigma radii, which means that the distributed error is very, very small. Next approach, trajectron, pretty much close in the radius of 1 sigma, 50%. But if we take a look at the split of forecast step by step, from the 1st to the 12th, one after the other, then we can see that the number of matches is changing radically, plus or minus 32%. Of course, we want to improve these figures. And in our work, we tried to make that happen. We have been using to forecast the major trajectory, the classic dynamics approximation method, and a small neural network that gives the final point to the dynamics approximation to build the trajectory. But since we're not trying to improve geometrical metrics, in this sense, any approach can work, any approach that generates the trajectory predicted by a human being. Next, trajectory is evaluated based on CovarianceNet. So for every predicted coordination, we add Gaussian distribution trying to estimate the error. Let's look at how CovarianceNet works. Here we have been using recurrent layers to code people in the scene, and the combination of attention of recurrent layers to code relationship between people. For example, if people are moving together in a couple, they're not trying to overrun one another or maintain distance. They're trying to be closer. That's an important piece of information. Next, we can use generative model and recurrent decoder for step-by-step generation of covariations of the error. Naturally, that is the sigma that we're trying to evaluate. So, we have processed this approach based on the same data set, and I have added the last line into the table. It's agreed, CovarianceNet, and we can here see that in addition to the fact that the number of matches is much closer to the normal distribution that we're looking for, that is 51% for 1 sigma radius and 93% for 3 sigma radius. In addition to that, they have very similar range, and they're almost linear throughout the entire step-by-step forecast. And below, there's the graph of distribution step by step for the matrix, where the dotted line shows for the 3 sigma values, And the simple line shows the 1 sigma distribution. In brown, we can see the normal distribution, and yellow and green are the projects of Rajectron and our approach. Let us note that Rajectron approach in yellow, with every step, goes down below, which actually says that when we expand the horizon of forecast, it's becoming overly confident, which means that people will be more often than not where we do not expect them, while our approach is quite linear, and it's actually very close to normal distribution. Let's sum it up. In this work, we suggested new metrics to estimate the forecast of the movement of the trajectory of a person. And it's been, by the way, picked up by researchers from Stanford as well, the authors of that yellow graph that you've seen. And they have published already the preprint of the article where they're trying to improve our metrics. Second thing that we have shown that for the time being, SOTA methods that we have been using are overconfident in covariance prediction. And thirdly, we have seen that proposed method for the more correct prediction of covariance. But most importantly, when we know the data in more detail, we can build a much more safe and quick trajectory for a mobile robot amongst people. Thank you for your attention.